All right, let's do some more from section 4.7. We're talking about optimization problems. We've done the first page here, problems 1, 2, and 3, and so let me get back to let me begin section problem 4 now. Problem 4, it says which points on the graph of y equals 4 minus x squared are the closest to the point 0, 2. Okay, so here's a picture. I've got a parabola that's facing down and then shifted up 4 units. And here's the point 0, 2, which is not on the parabola, okay? But I would like to find points on the parabola that are the closest to 0, 2. Okay, I'm going to call this point here xy. And of course, you know, by the symmetry of the parabola, I know I'm going to have points, 2 of them, in giving my answer. Well, let's see. So if I would like to know what points are the closest, I would like the distance from 0, 2 to xy to be as small as it could possibly be. So I'm going to have to go back to algebra for a moment and use the distance formula. The distance formula is the square root of the difference in the x's squared plus the difference in the y's squared. Okay, so for us that's going to be the square root of x minus 0 squared plus the difference in the y squared, that'd be y minus 2 squared. I want the square of the whole thing. Let's simplify. So we got the square root of x squared plus, when you FOIL, it actually, you know what, because we would like this to be a function of x, I don't want x and y floating around. I'd like to have only x. Y is 4 minus x squared, right? So let me go ahead and replace y with 4 minus x squared. That way everything is in terms of x. Okay, 4 minus 2 is 2. When you FOIL out 2 minus x squared times 2 minus x squared, that would be 4 minus 4x squared plus x to the 4th. Okay, now I've got 4 minus 4x squared, but then plus x squared would give me a minus 3x squared plus x to the 4th. And so here'd be that expression then in simplified form. Okay, now you could call this a function of x, which it is, and then at this point find your critical numbers and you know, continue the calculation. By the way, another option would be to make the problem a little bit easier by observing this. The distance is going to be the smallest when the expression underneath the radical is the smallest. So maybe to make this problem easier, why don't we just look at x to the 4th minus 3x squared plus 4. I'm going to call that f of x, and I'll minimize that expression. By the way, that would be a better way to handle this because then I don't need a chain rule, you know, when I differentiate and get my critical numbers. The conditions on x here are that x can be you know, all real numbers. I've got a polynomial. Okay, now I've got to get my critical numbers. So here's f prime of x is 4x cubed minus 6x. And 2x would be in common to those two terms. You can factor that out. The leftover would be 2x squared minus 3. Okay, when you set these two expressions equal to 0, you're going to have x equals 0 or x equal plus or minus the square root of 3 halves, which would be plus or minus 1.2 roughly. Okay, so now I've got to show that these values here, or figure out which one is the absolute min, right? So you can use either the first or the second derivative test. I'm using the first derivative test. And okay, I've got my table set up here and the number line, and I've got my 3 critical numbers marked on the number line. They're going to split this into 4 different intervals. And I'm ready to select my test values. So like if x is negative 2, that's in this first group. Negative 2 to the 4th is 16. Minus 12 is excuse me, negative, where are we at here? I'm not plugging in the right thing here. Negative 2 cubed is negative 8 times 4 is negative 32, and then plus 12 is negative 20. We're decreasing in that part of the graph. Okay, and then if I plug, let's use negative 1 in the next group, plug that in. Negative 4 plus 6 is 2, we're increasing. Okay, if x is 1 in the third group, 4 minus 6 is negative 2, we're decreasing. And then if x is 2 for the last group, 2 cubed is 8, times 4 is 32, minus 12 is 20. We're back increasing again. Okay, so we're decreasing, then increasing, right here twice. So that means that I'm going to have local min, 2 of them. Okay, and I care about the min points, right? Not a max point. So let's see here. The distance is going to be as small as it can possibly be when x is root 3 over 2 and negative root 3 over 2. Okay, and here'd be the proof of that. Now, these two mins are going to be exactly at the same height, so they are also absolute mins. Okay, the first derivative test just tells me where I've got local extrema, but the fact that these are at the same height means that they're absolute mins. Okay, and that's kind of what I was saying before. You know, that I mean, we're going to have 2 points to describe in our answer because of symmetry here, right? So if x is the square root of 3 over 2, square root of 3 over 2 squared is 3 halves. 4 minus 3 halves would be 5 halves. Okay, and yeah, so that'd be 1 point. Also, when you square negative the square root of 3 halves, that'd be 3 halves. 4 minus 3 halves is 5 halves. All right, so these 2 points would be the closest points on the parabola to the point 0, 2. Okay, and I mean, that would look about right. You know, if I were to plot these, I drew a picture. Looks like x is, you know, roughly 1.2, and y would be about 2.5. You know, so I mean, that looks right at least. In fact, it is right. Okay, you know, based on our picture there, we can at least conclude that that's a reasonable answer. I could have used the second derivative test in a problem like this. That would have been fine. That actually probably would have been quicker, right? Since f double prime would be 12x squared minus 6. That would be a fast calculation, and I could plug in my my 3 critical values rather than making a table. Okay. Either way, just make sure that you've shown your work for why the number is the min or the max. Okay. I mentioned in the last video that that is going to be something that I'll be grading you on. All right, let's take a look at problem 5 as another example. A rectangular page is to contain 24 square inches of print. The margins at the top and the bottom of the page are to be 1.5 inches, and the margins on the left and the right are to be 1 inch. Find the dimensions of the page so that the least amount of paper is used. Okay, well, this would be a real life problem, right? You're at a printing company. You don't want to be wasting paper. Okay, and so if you've already decided the amount of print that's going to be on the page, and along with the margins, like how exactly should the page look then? You know, should it be a longer left to bottom or right to left, or should it be a square, more of a square-like thing? You know, how exactly should it look? So I've drawn a picture. Okay, the area of the printed region is 24 square inches. The left and right margins are 1 inch. The top and bottom margins are 1.5 inches. Let's let y be the length of the printed region and x be the width of the printed region. Okay, so the area being 24 square inches of print would be where I take x times y. I'm going to let A be the area of the entire page. Well, the length of the page would be where I take y plus 1 is y plus 2. The width of the page would be where I take x is the width of the printed region plus 1.5 inches up here plus another 1.5 inches. That'd be x plus 3. A is a function of x, and I want to minimize the area, right? I want to find the least amount of paper used. So Where I see y, let me also rewrite that in terms of x. That'd be 24 over x, and I'd like to minimize a of x now. Okay, what do we know about x? Well, x can't be negative, right? X also can't be 0, because I know I can't divide by 0. So really all I know about x is that x is a positive. The fact that I don't have a closed interval means that I'm going to have to use either the first derivative test or the second derivative test. Okay, I'll be in section 4.3 here, not 4.1. Well, let's, in any case, we got to get our critical numbers. So a prime would be 0 plus 2 plus the derivative of 72x to the negative first would be negative 72x to the negative second. Or that'd be a minus 72 over x squared. If you add 72 over x squared and then multiply by x squared and divide by 2, x squared would be 36, so x would be plus or minus 6. X can't be a negative though, so throw away that number. And it looks like x is 6. Okay, now I got to prove that that is right. So let's use the second derivative test for this one, because the second derivative is very easy to calculate. Okay, we're going to have the derivative of negative 72x to the negative second. That would be 144x to the negative third, or 144 over x cubed. And I would say consider using the second derivative test whenever you can see that the second derivative is easy to calculate. Like the second derivative test would probably be a better option than what you saw over here. Still, this is okay, you know, the first derivative test. Just make sure that you're still showing the work that you got the right answer there. Now with the second derivative test, I need to plug in the critical value into the second derivative. X equals 6 is my only critical value, and when I plug that into a double prime, I get 144 over 216 is 2/3 when you reduce. That's a positive. Now the fact that a positive value came out of that means I have a local min at x equals 6. Now I need to know that that's an absolute min. Well, this local min is the only min, right? I'm not comparing this point to any other point. So in fact, this would be an absolute min also. All right. If x is 6, then 6 plus 3 is 9, and that would be the width that you'd want to go with there. And if x is 6, y would be, let's see here, if x is 6, y would be 4, right? 24 over 4 is 4 for y. And then 4 plus 2 is 6. Okay, so 6 inches by 9 inches would be the dimensions of the page that we'd want to work with so that the least amount of paper is being used there. Maybe let's, well, you know what, I'll go ahead and stop the video right here for this one.